No, I don't see people going out, so I'm pretty sure.
Good evening, everyone. Welcome to another session of the Network Webinar series, hosted by the Center for Network Intelligence at the ECE and RCCPS ISC. Today's talk is by Dr. Karthik, and we will be speaking on almost optimal based Restless Markov or identification with fixed confidence. Dr. Karthik is a research fellow in the Institute of Data Science at the National University of Singapore, where he works with Professor Vincent Tan. Prior to joining NUS, he obtained a PhD and MSc Engineering dual degree from the Department of Electronic Communication Engineering at IISc Bangalore with Professor Rajesh Sundarshan as his thesis supervisor. Much earlier to joining the dual degree program, he worked as a project assistant in Professor Chandra Armurthy's lab at IISc. He graduated with a Bachelor of Engineering degree in Electronics and Communication Engineering from the College of Engineering. Before we move on to the talk, we request the online audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may raise your hand or unmute yourself, or you type them in the chat box. The talks will relay your questions. And for in-person audience, we have arranged for refreshment at the coffee lot. Please help yourself after the talk. Over to you, Dr. Karthik.
Is this running?
Audio.
Yeah, it should be okay.
Okay, you can just alert me.
Yeah.
Okay, thanks everyone for this opportunity. I think 2020 Jan or February was the last time I gave the in-person talk in IISc. It's very good to be back. So today I'm going to talk about a piece of work that I did collaboratively with Vincent, who is my postdoc supervisor at NUS, and also with Ali, who is at RPI in New York, and Ali's student, Arpan. So I will dive right in. The setup is that we look at a multi-arm bandit with K arms. On the figure, on the slide, K is 4. So there are 4 arms. For those of you who don't know what a multi-arm bandit is, just think of it as a number of choices to play with at each time instant. So here there are 4 choices. Now by a choice, I simply mean a process. Each choice yields a sequence of random variables. It's a process. For the purpose of this talk, I am going to look at this as a Markov process. Okay, it's a Markov chain. So each of these options or arms, so to say, is a Markov chain. It's a discrete-time Markov chain. And the specific setting that I'm going to look at is what is called restless Markov chain. I'll describe what that is. But before that, each of these Markov chains is assumed to be taking values in a finite state space. So it's a finite state DPMs. Each of these, we assume that the state space is common across all the arms. P1, P2, P3, P4 indicated at the top denote the transition probability matrices of the respective arms. So this process x0, 1 up to x7, 1, whatever I indicated, that the state transitions are governed by P1. Similarly, the state transitions of the second arm are governed by P2, and so on. Now, of course, all of these are the set of all possible observations that one can collect. But let's say you are a learner and you are interested in finding something about the system, which I may emphasize. You don't get to observe the entire system. So the system is restless in the following sense. So let's say at time n equal to 0, you observe option 1 or arm 1. Hereafter, I'm going to use the term arm to denote the option. So let's say you observe arm 1, and the observation that you collect is, let's say, x0, 1. The first subscript will indicate time, which starts from 0. Second subscript will indicate the arm index. So let's say you collect x0, 1. Now at time n equal to 1, let's say you select arm 2. You did not observe x02, but you observe only x12. So arm 2 has already evolved by 1 time step. Let's say at time 2, you selected arm 3. You did not observe the first 2 observations. You directly observe x2, 3. So arm 3 had already evolved by 2 time steps. Let's say x34's observation from arm 4. Let's say similar observations are collected. The point to note from this slide is that irrespective of whether you choose an arm or not, the arm continues to change. That is the setting of restless arms. It is in the sense that I am saying that the arms of the system is restless. It continues to change whether or not a particular arm is observed. Okay. All of this is there. The main goal in this problem is what is called fixed confidence best arm identification, the details of which I'm going to present on the next slide. So formally, we will consider a K-armed bandit. Okay. So these are the K arms or the options. In the figure, K is equal to 4. Each arm for us will be a homogeneous discrete-time Markov chain taking values in a finite state space S. The state space is assumed to be common to all the arms, so that the arms cannot be distinguished without observing them. Okay, so just merely by observing, if the state spaces are different, merely by observing a certain state, one could possibly tell this is the arm, but that's not allowed here. State space is the same for all of them. Okay. The arms of the system is restless in the sense that I described on the previous slide. We assume that each arm is governed by a transition probability matrix. Let's denote that as PA corresponding to arm A, where A goes from 1 to K. In general, K is equal to 4 in the example. Now, we only place a mild assumption on the transition matrices, which is that they are ergodic. Ergodic, in simple terms, is irreducible, aperiodic, and positive. Okay. So, associated with each ergodic TPM is a unique stationary distribution or the invariant distribution. Let's call it mu A associated with TPM PA. The transition matrices and the stationary distributions mu A are unknown. Let's say you are the learner, it's unknown to you. Now there is a function f which is defined on the common state space of the arms. Okay. Now this is a real value function, and associated with this function is the mean reward of each arm. Okay. The mean reward is simply the average value of the function f computed under the arm's stationary distribution. So I is some state in state space S. F of I is the value of the function at this particular state. Mu A of I is the mass that the stationary distribution of arm A puts on state I. Average it out across all I, sum it up across all I. That's the average reward of arm A. We do this for every A, and the best arm is defined as the one which has the largest mean. Notice that the best arm is a function of the stationary distribution, which is not known. So the best arm is not known a priori. The goal is to learn what the best arm is. And there is a certain specific objective that we look at in order to identify the best arm, and that specific objective is what is called the fixed confidence objective or the setting of fixed confidence. Before I describe that, so here is a particular selection of arms. Now, you could keep going further until some point, let's say you stop. And at the point where you stop, you decide to output which is the best arm. So your output is going to be a number between 1 and k, which indicates the best arm in your judgment. So we don't want to make too much of error as well. Okay. So these are some things to keep in mind. One thing is we do arm selections like these. We keep going until some point where we stop. Hopefully we will stop. So let's say pi is some policy for identifying the best arm. Let's say tau pi is the random time at which this policy stops. Okay. Ideally, for the problem to be verified and for the policy to make sense, we should at least stop in finite time with probability 1. If we are not going to stop, it's not a very meaningful policy. So we will impose that we want the stopping time to be finite probability 1 to begin with at least. And the fixed confidence regime is that we want to identify the best arm correctly with error probability at most delta, where delta is some fixed value which is given upfront. Now, of course, the error probability will depend upon what is the instance. The instance, by an instance, I mean the choice of P1, P2, P3, P4. If I tell you what the P1, P2, P3, P4 is, you know what are mu1, mu2, mu3, mu4. Therefore, you know what the eta1, that is the mean reward of R1, eta2, eta3, eta4 are, and therefore you know the best arm. So, to find the best arm, it suffices to specify P1, P2, P3, P4, which together collectively I call as an instance. Now, the instance is not known, and the policy has to find the best arm without knowing the instance. When I say that the error probability of the policy can be at most delta, it can be at most delta no matter what the underlying instance is. So we want it to be at most delta no matter what the instance is. So for example, If P1, P2, P3, P4 is the instance in which P1, let's say R1 is the best term, that's what I have boxed there, then R1 should be identified correctly with probability at least 1 minus delta. The incorrect arms should be identified with probability at most delta. I'm not saying you are not about to make error, you can make error, but the error probability should be at most delta, where delta can be however small we want it. Similarly, if the instance is changed, Q1, Q2, Q3, Q4 is the actual instance where the fourth arm is the best arm. In that case, we want R4 to be identified correctly with probability at least 1 minus delta, and with probability at most delta, other arms can be identified. So this is the restriction. This is what is called the fixed confidence regime. So this means that we should identify the probability of identifying the best arm incorrectly. A pi is the best arm which is output by policy pi. It is a number between 1 and k. That is not equal to A star, which is the true best arm. The probability of this happening, this is the error event. We don't want this to happen too frequently. Probability of error should be at most delta. Delta is something which will be given to you. Delta is something which will be specified beforehand. You need to design policies that ensure that the error probability is at most delta. Of course, you should also stop with finite time. If you don't stop, if you take infinite time, you can identify any risk. So it won't be very meaningful to allow infinite time. We want finite time. You should stop in finite time, and you should output the correct answer with probability of error at most delta, or with probability of correctness at least 1 minus delta. So this is what is called the fixed confidence setting. Suppose pi delta is the set of all such policies which are of interest to us. That is, which stop in finite time and which identify the best term correctly with probability at least 1 minus delta. Suppose pi delta is the collection of all such policies. These are the policies we want. We want to come up with a policy like this. And our goal is, not only do we want to come up with a policy like this, but that policy should identify the best term in the smallest time possible. It should take as less number of samples like this, as less time as possible. It should identify the best term correctly with probability of error at most. Stop in finite time. Not just stop in finite time, stop in as less time as possible. So in this sense, in the expected sense. So this is what we call as a problem of fixed confidence. By fixed confidence, I mean fixing the confidence level delta. Fixed confidence, best arm identification. Identifying the best arm. So each of these is a Markov process. There is a function which is defined. Average value of that function is the best. The best arm is defined with respect to the average value of the function. So this is the problem. I hope the problem setting is clear. Our analysis or our goal will be to analyze the value of this quantity as delta goes to 0. As the error probability becomes smaller and smaller, intuitively this quantity should grow. It should increase for the simple reason that lesser the room allowed for error, the longer you may potentially have to wait before declaring the answer. Because you have to declare it properly, because the allowed room for error is very less. So you better be correct when you declare the answer as much as possible. So intuitively this will grow with delta. That is, as delta decreases, we expect that this quantity will increase. How does it increase? At what rate does it increase? Is there a policy which will match this growth rate? These are the kind of theoretical questions that we are interested in. Okay. So it turns out that in the analysis, to make this whole setup amenable to analysis. So here I describe a very generic setup where the transition probabilities are P1, P2, P3, and P4. This can be any arbitrary transition matrices. They need not have a specific structure. We are not saying that every entry of the transition matrix should be strictly positive. We are not saying anything like that. These are just generic transition probability matrices. The only constraint is that they should be ergodic. That's all. Irreducible, aperiodic, and positive return. These are the only conditions we place. So it turns out that in order to do the analysis, I mean, you can as well expect this, but in order to do the analysis, you as a learner will be able to observe only these colored quantities. Only using these observations, you should infer what is the best term. So the most natural thing to do would be to estimate these matrices itself in the first place. Try to estimate the transition matrices. That is, you count how many times I to J transitions have happened, how many times I transitions have happened, and so on. So you can construct estimates for the transition matrices. But it turns out that when you do that, the estimated transition matrix may not be ergodic. There is no guarantee that it will be ergodic. Therefore, there may not be a stationary distribution associated with that estimated transition matrix. Therefore, you may not be able to compute the best form under the estimated transition matrix. So there are all of these issues which will come in when you do the analysis. So to circumvent all of these problems, we impose a certain exponential family model on the transition matrices. So what we do is, instead of assuming that P1, P2, P3, P4 are some arbitrary transition matrices which are governing state transitions on the arms, we will impose a specific structure for P1, P2, P3, P4. The specific structure comes from an exponential family, which I am sure most of you know in the context of Poisson, Gaussian, and all of that. Those are for IID observations. This is an exponential family for Markov chains. So the exponential family, to construct this exponential family, you start with three quantities. One is a parameter space, which is known to you. For example, the parameter space can be the interval 0, 1. Okay. You start with a transition matrix P, which is irreducible. This will be called as a generator for the family. You also start with a reward function F. Now, starting from these three, you construct, the first step is to construct P tilde theta, which is a matrix now, given any theta belonging to the parameter space. So given any scalar parameter theta, you construct a P tilde matrix, which is obtained by an exponential tilde of the generator P. Take the generator P, apply an exponential tilde to that in the form of e to the theta f of j. You arrive at P tilde theta of I comma j. Notice that P is a transition matrix, which means its rows sum up to 1. Each of its entries is non-negative. The rows sum up to 1, but the rows of P tilde theta will not sum up to 1. So what we do is we will normalize it appropriately and we turn it into a transition matrix whose rows sum up to 1. The way we do that is, from P tilde theta, we come to a P theta in the following way. Associated with P tilde theta, we can show that there are eigenvectors u theta and v theta, such that u theta is the right eigenvector and v theta is the left eigenvector, associated with an eigenvalue rho theta, which is called the Perron Frobenius eigenvalue. The P of eigenvalue can be shown to be strictly smaller than 1, and this particular quantity, using the u theta and the v theta, in particular using the v theta, we can construct P theta. Okay, this is just a model, just follow me. With theta, we construct a P theta in this form. What is the advantage? The advantage is that for every theta, P theta is ergodic. The model guarantees that. Which means P theta is associated with a unique stationary distribution, mu theta. And mu theta also has a specific form. It comes from component-wise multiplication of u theta and v theta. U theta is a vector. Okay? V theta is a vector. Both have the same length. Multiply component-wise, you get a new vector which I call mu theta. That happens to be a probability vector. You can show that. So associated with P theta is a unique stationary distribution which I call mu theta, which has this particular form. Not just this, more importantly, if you look at the mapping from theta to eta theta, remember eta theta is the mean, average mean associated with P theta. The reward function f is there. Average value of f under mu theta is what I call eta theta. If you look at this mapping, this is a bijection. It's a strictly increasing function. Okay? Which means it suffices to estimate the mean in order to get back to the parameter. So remember, on the previous slide, I showed you some observations. Using those observations, in particular for any particular arm, okay, I'll go back. For any given arm, let's say for arm 2, you will have x1, 2, x6, 2, and so on. If you keep going, you will have additional observations. Just using those observations, you can estimate the mean of that arm and you can invert that mean to get back to the parameter of the arm. So that's the next thing I want to say. Now the instance is going to be defined not by arbitrary P1, P2, P3, P4, but under the exponential model, it will be defined by theta 1, theta 2, theta 3, theta 4.
So this f you use, right? In the exponential family, the same f you're using the word.
Yes. Same.
So what is the reason? This seems like everything else I'm okay with. This is general, too specific. Right?
No, the reason is that I want to define the average value under F. So the mapping, so P theta is associated with the mu theta, and I want to define the average value of F under mu theta. So it will be a bijection only under the same F because the F is coming here.
So here you are getting some information by observe about the transition probabilities by observing the rewards.
Yes, yes. That is the information we have to exploit to estimate the matrix. Estimating the matrix now is equivalent to estimating the parameter. If you know the parameters, you know the matrix. Because we know the mapping from theta to P theta. This is all something we can do offline in team building. If you know the theta, you know the corresponding P theta, you know the corresponding mu theta, you know the eta. So that mapping is already known. All you have to do is estimate the theta somehow.
So, but this u theta and dot, the theta element-wise product, right?
Yeah.
It's a complicated function of F, right? Because I don't know what the eigenvector will look like.
Right. I mean, this is the these are the right and left eigenvectors associated with the column for
The second largest eigenvector. So, which I understand, but it still be some complicated function of F, right? It's not straightforward.
Right.
For that.
Actually, I'll come to the computational feasibility of this whole.
It's okay, I'm just trying to understand. And then bijection from what? Theta to eta theta is what you said is the bijection?
Right.
So,
So
increasing function of theta. That's
yes. So in fact, I'll be more explicit. What will happen is this eta theta, if we look at the average value of F, F takes only finitely many values because it's a function of a finite state space. So let's say the minimum value is small m and the largest value is capital M. This is a number which will likely interval small m comma capital M. All I'm saying is between the set capital theta and the interval m comma capital M, this is the bijection.
Saying that you're assuming each event to be of this form,
Of this form.
and you can compute the average. Get back to
Get back the parameter.
each event corresponds to different event. Or
No, that is the uniqueness. Corresponding to, so I'm saying that this is the bijection, which means it is 1-to-1.
I think not. So you see that function there, right? So for theta 1, you will get the same Pij for theta 1 fj. For theta 2, you will get Pij for theta 2 fj. So only theta changes, everything else remains same, f remains same.
F is constant. F doesn't change with theta.
That's the same function he's using for reward and the same function he's using to generate the probability constant.
So this mapping is a 1-to-1 mapping, which means there is exactly one theta. So if you estimate the mean, there is exactly one theta which has that.
Why the uniqueness is not clear, like I can see increasing, but but you're saying that if I change, theta, I may not get the same mean, right? I don't see it.
I mean, actually, it is very similar to the usual exponential family. The Gaussian, whatever. I mean, mean with parameter theta is exactly the same as that. It's just that because of the theta fj, the exact roots is a little complicated. So the objective restated is to estimate. So is that the instance is now specified by theta 1, theta 2, theta 3, theta 4. Okay, and the theta vector is now unknown. Earlier we said P1, P2, P3, P4 are unknown. Now we say that theta 1, theta 2, theta 3, theta 4. This vector is now unknown. This is the one which defines the instance. If these are specified, the best are. Okay, and A star is of course R max of theta, theta A. Theta A corresponding to R. And the goal is still fixed confidence best on. So it turns out that in the analysis of this system, which I said is a restless system, there is now what I'm going to describe is a certain Markov decision process which will play a very, very important role in the analysis. So here is the Markov decision process. Now suppose that the system has evolved up to time 7 in this particular manner. I've just indicated some sequence here. It can be anything. But let's say it has evolved in this particular manner up to time n equal to 7. At time n equal to 8, an arm is yet to be selected. Okay, at each time instant, the learner picks one option. The learner then gets the observation corresponding to that option. This process keeps repeating. Option, observation, option, observation. It just keeps repeating. So suppose at time n equal to 8, the observer or the learner is yet to make or yet to select an option. At that point of time, I would like to bring your attention to two quantities that represent the state of this entire system. And that is what I call an arm delays and lost observed states. So what are arm delays? Let's say we are at time n equal to 8, we will ask ourselves, how many time instants ago was each of the arms selected previously? So relative to time n equal to 8, I will say that the delay of R1, which I denote as D1 of n, is equal to 1. That is because R1 was observed previously at time n equal to 7. At that point, the corresponding observation it was obtained was x71, which is the last observed state of R1. Similarly, relative to n equal to 8, the delay of R2 is equal to 2, because R2 was observed at time n equal to 6. Last observed at time n equal to 6. Because 7 was not observed, right? At time 7, R1 was selected. So the other arms could not be observed. Yet they continue to work. So the delay is equal to 2. At that point, the corresponding observation was x62. The delay of arm 3 was 3 because it was observed at time n equal to 5, which is like -3 instead of above. And the corresponding observation was x53 and so on. So you can repeat this in fact. Let's say at time n equal to 8, based on all of this observation, let's say the learner, and you as a learner decided to choose R2, let's say. So you got an observation, let's say x82. Now you have to update the delays and last observed states based on this information. The delay has now increased to 2 because it was observed at time n equal to 7. It is 2 time instances ago, relative to 9. This is 1 because it was observed at time n equal to 8. The corresponding observation changed. And so on. So this just keeps repeating. At time n equal to 10, also you can just do the same thing. So the delays of all the unobserved arms will increment by 1. The last observed state will only change when the corresponding arm is observed. Otherwise, it won't change. So it turns out that if you connect the dn and the in for any given n, in other words, for any given n, you look at this row, connect that into a vector. Look at the corresponding row here, connect that into a vector, stack these two vectors next to each other. That, it turns out, is a controlled Markov chain with controls as the option selections or the arm selections. So let's say at some time n, dn, in was the representation of the system. Based on that representation or based on that information, you as the learner selected arm an. Based on the selected arm an, the dn and in got updated to dn plus 1, in plus 1. Just like how d9, i9 got updated to d10, i10. Okay? And then some arm an plus 1 was selected. Based on the selection, dn plus 1, in plus 1 got updated to dn plus 2, in plus 2. This keeps continuing until a point where it stops. So, in other words, this is a controlled Markov chain, or in other equivalently, this is the Markov decision process where the state space is the space of all possible values of the di vectors. Now, the d vector, which is one particular row of this table, has positive integer values with exactly one of the components equal to 1. The component equal to 1 denotes that the particular arm was chosen in the previous times. Only one of the arms can be chosen at any given time. Therefore, exactly one of the components is equal to 1. All the other components will be strictly bigger than 1. And they will increment in a deterministic way. If they are not selected, if an arm is not selected, its delay will simply increment by 1. So the delays and the last observed states take values in a countable set, which is a subset of the set of integers to the k to account for k arms, and the state space of each arm raised to the power k, which denotes this vector. The value set in which this row takes values. Okay, so this is a countably infinite set. Next, the action space of the MDP is finite. What is the action space? The action space is simply the space of options of the set of arms. There are k arms. The learner chooses one of these at any given time. So the action space is a finite set. One can of course write down the transition probabilities of this MDP, which are of the form: given a current state and an action, what is the next state? The probability of this. The conditional probability of given a current state and an action, what is the next state? I don't want to read out the specifics, but what I want to point out is that there is a power which comes here. Okay. So in particular, there are transition matrix powers which appear in the transition probabilities of the MDP. These transition probabilities depend, of course, on the transition probability matrix of each of these arms. They depend on the theta values. They depend on the underlying instance. And there are powers of these matrices which will appear in the expression for the transition probability matrices. Just remember this one now, the TPM powers appear. I'll highlight this point later also.
One question.
Yeah.
Is there a requirement on the order of options to
Order in the sense,
which option you choose at every time step?
it can be any one of these.
The example is misleading if you're sort of taking them right.
So initially, I simply assume that each of the arms is observed once. It may not necessarily be in the order 1, 2, 3, 4. It can be in any order. For simplicity, I assume that it's 1, 2, 3, 4, but we assume that we don't miss anyone. We observe at least, we observe each of the arms at least once, and we assume that each of the arms is observed once in the first k time instance itself. It doesn't matter when, but we assume that it's observed.
And afterwards, is there some random choice or
It can be deterministic or it can be a randomized selection. Yeah, that is the heart of the problem. How do we select the arms? And the selection of arms should be in sync with a certain objective that we want to achieve. And that objective is the fixed confidence Western identification, whatever I indicate. So I will precisely state that.
I think what is asking is a constraint like locality constraint. We cannot go too far away.
Okay. I will come to that. So, yeah, so these are the transition probabilities. It turns out that these DI values, so to say, they naturally satisfy a certain flow conservation requirement. Okay. What happens is the system is in a certain state, Dn In at any given time. An action Am is chosen and the system enters Dn plus 1, In plus 2. An action is taken, the system enters Dn plus 2, In plus 2. So it's as if the system is leaving a certain state, entering a new state. Leaving that state, entering a new state. Leaving that state, entering a new state. So every entry is matched by an exit with respect to the DI state of the system. So that is something that we have to capture very carefully before we derive the theoretical results. And that can be captured in the following way. If we mathematically write down what is the total number of times the system was in the state Di, some Di, system was in the state Di, and an action A was chosen up to a time N. And for the system actually in the state Di, if we look at these two quantities, these must satisfy a certain constraint with this. This is easy to show. In particular, this quantity represents the total influx into the state Di. That is total flow, inward flow into the state Di, and this can be interpreted as a total outward flow. And the outward flow and inward flow should match. Essentially, this is just a restatement of the fact that the system enters a new state, leaves that state, enters a new state, leaves that state, enters a new state. So every entry is matched by exit. That's all it is. Okay. The one is simply to account for the fact that if you stop at some point, you only enter, you won't exit over that. And the first state you started with, there is only an exit now. It's just to account for that there is a one. Okay. Okay. So this is the question that Peter was asking. So here what happens is we can select the arms in any arbitrary fashion. I have not imposed any constraint on that. So let's say after some point of time, we simply choose to focus or we simply choose to select a particular arm. Let's say we always choose arm 1, starting from time 10 onwards here. Let's say we always choose arm 1. In that case, what will happen is the delays of all the other arms will continuously keep increasing. It will just keep blowing up. Okay. So as such, this is a countable state MDP, like I already mentioned, because the arm delays are integer values. They can be arbitrarily large. So it's very difficult to analyze this countable state MDP, and for the purposes of making this problem amenable to analysis, we will make a finite state reduction of this countable state MDP. Okay? And the way we do that is we are going to impose a constraint saying, we will fix a particular integer R, potentially large, and we will forcefully pull an arm if it has not been observed for R consecutive time instants. So if there is any R which has not been observed for a long time, by long time I mean for R time instants, in the next slot I will forcefully sample that. That way I am resetting the delay of that arm to 1. Because whenever an arm is selected, its delay becomes 1. So I am restricting the arm delays to take values between 1 and R, 1 and R, 1 and R. Is this a good representation of the original system? No. This is a significant simplification. It has made the state space of the MDP finite, whereas the original MDP state space was infinite, countably infinite. So how does that affect the analysis at all? We will see. And did we forget the original problem? I will come back to it. How does the analysis for the finite state MDP? What does it tell us about the problem hardness or the theory for the original countable state space MDP? I will come back to that. For now, we will assume that this is the case. Okay. So for the remainder of this talk up to a certain point, I will assume that there is an R which is also given to us just like delta. The R will tell us what is the maximum duration for which we are allowed to select. We are allowed to not observe an R. If you have not observed an R for more than R time instance, you better observe it in the next time instance. And because of the manner in which we are going, because of the manner in which we are selecting the arms, exactly one arm's delay will become equal to R. If at all it becomes equal to R. 2 or more arms delay cannot become equal to R at the same time. Okay, so that way we have said it. So now the state space of the MDP, which I earlier wrote as S, that was the countable state space, I am now writing it as SR to denote that all the arm delays are between 1 and R. So here notice that if the system has a dn in value at any point time n, such that the component of D vector has one of the arms equal to R. The delay corresponding to one of the arms, any one of the arms is equal to R. Let's say in particular arm A, some A, it's equal to R. You have to select that upon this. There is no choice. Okay. Because of this constraint on the state action transitions, the transition matrix of the MDP will of course depend on R. Okay. For the simple reason, this is a snapshot of the table from the slide I showed before. There were no constraints, because of which the row corresponding to n equal to 10 looks like this. But if R is equal to 6, then that means that arm 4 delay has already become equal to 6 at time 9. At time n, we have to select. So this particular row will not appear when R is equal to 6. So this is just to say that Q theta, which is the MDP transition probabilities, will depend on R also. Under this new constraint, that is the R max delay constraint. This is what I call as the R max delay, maximum delay. Delay means R delay. So R is the value of the maximum delay. So R max delay constraint plus flow constraint will look like this. The only change is that there is an R here and there is an R here, there is an R here. That's the only change. With this, the new objective is as shown here. Fixed confidence best form identification, K choices. Each choice is specified by a theta K or theta A. Okay, and the thetas as such are unknown. There is a best form. We assume that the best form is uniquely specified. And then our objective is to identify the best form in as small time as possible by ensuring that the error probability is at most delta and we respect the R max delay constraint. The flow constraint are not including because every policy will satisfy the flow constraint. Okay, so this is the objective. This is the problem that we are attacking. We want to understand how this quantity grows with delta and with R. Okay, so now I'm going to present upon this, which is the lower bound of that. So let us fix the theta. Assume for simplicity that the best arm is R, and the theta, R1 is the best arm. Now the like this. Intuitively, we expect it to grow with delta. We'll see whether that happens. There is a constant PR star which appears, which has this particular form, and there is a sigma r of theta which appears in the expression for PR star, in particular in the supreme. I'm going to spell out the details of each one of this. So, first, we are saying that this grows with delta. At what rate does it grow with delta? We can show that it grows as logarithm of 1 over delta. From Chernov's work, it's from the time of Chernov's work, error probability and time always have an inverse exponential relation, but is still respected here. And this expected stopping time grows as logarithm of 1 over delta by PR star. PR star is a certain problem hardness. Okay, I'll tell you what the PR star is. In particular, when we look at delta going to 0, we can believe that this is the correct growth rate. Okay, there is a growth rate. Is this growth rate good enough? See, you can always argue that 0 is a lower bound. Okay, you can always say infimum over pi belonging to pi delta, E of pi, expected delta of pi is bigger than or equal to 0. Always, because expected stopping time is always bandit. But is 0 a good lower bound? No, because you cannot do it 0. Okay, unless you are given, unless the instance is, but is 1 by PR star a good bound? We will see. Okay, that's a question to ask. So, this is the first part of the lower bound. The second part is about the constant PR star itself. PR star, notice, is the solution to a soup-in optimization problem. Recall that these are the MDP transition probabilities under the R max Dirac constraint. Okay. So here the interpretation for this is that there is a game going on between the learner, which is you, say, and the environment. Now the environment presents itself with instances. There is a ground truth which is not known. There are alternative instances where the environment tries to confuse the learner into believing that the best star is not the best star in the ground truth, but something else. Those are the bad instances. So those are all the alternative instances. There may be many such bad instances, and the learner has to fight against all of those bad instances in order to arrive at the best star correctly. Now, what the learner can do is the learner can only select options. Okay, select an option, get an observation. Select an option, get an observation. This is all the learner can do. When the learner selects the options, the system state is also involved in the The system enters a particular DI, leaves the DI, enters a new D prime I prime, leaves the D prime I prime, enters a new D double prime I double prime, and so on. The DI, that cycle keeps continuing. Although the learner can only control the A part of that, the learner only has control over which option or arm to select. It is very important that the DIA fractions appear in the correct fraction. I mean, the DIA values appear in the correct fractions. So, although the environment is trying to confuse the learner is trying to maximize the information discrimination by choosing actions in such a way that the new DIAs are maximized. So, in other words, this is what the learner cares about. The environment is trying to confuse, which is by the infimum, and the learner wants to keep this confusion at a minimum by maximizing the information discrimination. So, okay, so this is just a small detail that the K divergence term here involves powers of transition matrices that I already mentioned. Okay, and the scale divergence is really about row-wise scale divergence added up all together. Okay, so this is a transition matrix of the MDP under the instance theta. The rows correspond to DIA tuples. The columns correspond to D prime D prime.
I think what you get is that how do you naturally get this, this minimax problem,
So this is an artifact of the data processing. So what happens is,
so what is the objective like? I'm trying to see how you arrive at this. New DI, I understand. That's the fraction of if you play an action for every DI I play an action, right? That's the average number of such tuples I will get, right? And then how do we this
what we do is when a particular action is selected, we try to understand. For instance, if you focus yourself on R3, we try to understand what is the probability of transitioning from 5-3 to 9-3 under a particular instance theta versus an alternative instance lambda.
Oh, okay. Also, you're saying that the estimate I have every time is lambda. So either it's coming from minimum, it's coming from lambda if I don't know any particular.
Yes.
And then how bad it is.
Yes. So those are the powers that are here, and that power I have just captured it as a transition matrix of the MDP. So in particular, this is the power and this is the information distribution what they do. And the last thing is the supremum in this expression sigma r theta is computed over the space of all probability distributions on DIA, collectively on DIA. Although the learner can only control the A part of it, it's collectively on the DIA. First two lines simply says it's a probability distribution. Third line says it's the flow constraint, which is automatically satisfied of every policy, and the last line says it is the R max delay constraint. Slightly convoluted way of writing. So this is what it is. In particular, sigma r theta is a closed set. It's a subset of a probability distribution, a subset of the probability simplex of the DIA space, which is now finite thanks to the R max delay constraint. So it's a compact set. So the supremum is being taken over a compact set. What about this particular inside function? If that's continuous, we are in business. So we know that that's indeed continuous. So if you look at the inner infimum term, that as a function of its arguments, it can show it's continuous, and the continuity is a slightly different version of that versus maximum theorem that's applied specifically to non-compact sets. The non-compactness is coming from odd theta. Odd theta is non-compact. So psi is continuous because we have a continuous function which is being maximized over a compact set. The maximum is certainly attained. We don't know whether it is attained uniquely. Forget that. We will consider the set of all maximizers. Let's call that as W star of theta, corresponding to any instance theta. We can show that this set value mapping theta to W star theta is upper significant. That will play a very important role in the achievability, which I will come to later. Achievability is all about answering the question, how good the lower bound is 1 by TR star. I showed you a lower bound on the previous slide, which had a limit delta going to 0, and there was a lower bound of 1 by TR star. We could have as well written 0, but 0 is not a lower bound. Is 1 by TR star a good lower bound? In other words, can I achieve it? That's the question. So for achievability, this is very important. And the key idea for achievability, which I want to bring your attention to, is that these fractions, and these are the fraction of times DIAs occur. These are the fractions in which the DIAs occur in the system. Remember, the learner is selecting those observations, those options, observations, and behind the scenes there is a DI changing to like a DNIN changing to DN plus 1, IN plus 1, changing to DN plus 1, IN plus 2. All of this is happening. So you count how many times DIAs are happening inherently behind the scenes, and you look at the fractions of the DIAs. We will show that these DIA fractions, when collected as a vector, that will converge to this set. This is a point to set convergence. Okay, so we will show that it converges to the set, and that's what we want. If there was a unique maximizer, we would have shown that this vector converges to that unique vector componentless. This is what they are saying, that in the super sense it's converging to this set. Okay. So I just want
multiple elements.
right. I mean, it's a set
Of elements.
right?
Typically, law of large numbers is gonna go to like one, right? Measure, right? You're saying that multiple.
So you look at one
W star theta is a set of
set of combinations. You look at one particular element mu from that. Take the component wise difference between that vector and the new vector, and take the maximum of such components. And you look at the smallest, the distance from that vector to this, the smallest distance from that vector to this. Or in other words, it's the distance from this vector to the projection of the vector on this. Okay, so I just want to compare this complexity that we arrived at with the complexity, the corresponding complexity terms from the prior words. So this complexity was for the setting of restless arms, which, to recall, simply says that the system evolves irrespective of whether or not the observer or the learner selects a particular arm. Even if an arm is not observed, state evolutions continue to happen on that arm. That is what restless means. In the literature, simpler settings have been studied. In particular, rested arms setting here. It's like you're working on K projects in parallel. At a time, you can work on one project. If you don't work on a project and make progress, the progress on that project is stalled. That's the setting of rested arms. If you don't observe an arm, the state transitions on that arm are frozen. That's the setting of rested arms. In that, there is a very similar term that comes, a soup-in term. It's just that in the KL divergence that comes in the problem hardness, there are no transition matrix powers. It is free from transition matrix powers. Why is that? That's because only when you select an arm, the arm will change. So it's as if the arm delays are equal to 1. You observe all the arms at all times. It's as if it's like that. Although you observe only one arm at a time, because the arm changes its state only when you select it, there is no loss of information. Because of that, there is no powers of transition matrices, and that's significantly simplified. The absence of TPM powers significantly makes the problem easier. Whereas the presence of TPM powers, which I have not indicated explicitly, I have indicated implicitly via the transition matrix of the MDP. Okay, which depends on the powers of the transition matrices of the arms. So please don't, I hope I'm not confusing you with two sets of TPMs. One is the TPMs of each of the options, theta 1, theta 2, theta 3, theta 4, give rise to P theta 1, P theta 2, P theta 3, P theta 4. Those are separate. With those, you can construct a transition matrix for the MDP itself. That is a different transition matrix. That is what this is. It's not P theta, it's Q theta. Okay, it's for the MDP. So, yeah, this is for the rested arms. And an even simpler setting is IID observations. That is, each arm yields, let's say, IID Poisson observations or IID Gaussian observations. In that case, the transition matrix itself will have identical rows. All the rows will be the same because IID process is a special case of a Markov process. So, in that case, the KL divergence is a very even simpler expression. So, in the prior works, the simplification of the inner uniform term and the analysis of this whole complexity is much, much simpler than it is in the restless system. Okay, so this is what I just wanted to highlight. How am I doing on time? Sorry? Oh, okay. So I want to tell you about achievability. That is, how can we achieve the lower bound? So, in order to achieve the lower bound, I will come up with the policy now. The policy will have a uniform policy embedded in it. Okay. Uniform policy is simply selecting the arms uniformly at random, but respecting the R max delay density. That is, whenever the delay of an arm reaches R is a certain value given to us beforehand, we have to forcefully select the arm. There is no option. Otherwise, we can select uniformly at random. Under this random policy, notice that this is a policy which doesn't depend on time. It is independent of time. It's a stationary policy. Under a stationary policy, you can show that a controlled Markov chain will become a Markov chain. A controlled Markov chain is what? Under the controls, it's a Markov chain. But when the controls are stationary, the original control Markov chain itself becomes a Markov chain. And you can write down a transition kernel for the Markov chain. It turns out that this transition kernel is ergodic. Okay. So therefore, it will have a unique stationary distribution, which I call as mu theta uniform. And associated with this uniform distribution, which is a distribution on the DI space, everything, all of this is for the MDP. Okay, nothing for the arms. Arms is not clear. All of this is for the MDP. So this is on the DI space. You can multiply the DI with the A given DI like this, and you can get a DIA joint. This is what we call as the ergodic occupancy measure, ergodic state action occupancy measure. So generally, when I say state, you should think of DI because I'm referring to the state of the MDP. Action is A. So DIA together is state action. Okay. So all of this is there. Why is that useful? I tell you. So here is the policy. I'll try to do fast. So here is the policy. It will have 4 components to it. First component is the most natural component, which is estimating the parameters of the arms. That is what we don't know, right? The problem instance is specified by theta 1, theta 2, theta 3, theta 4 in the figure. If you know theta 1, theta 2, theta 3, theta 4, the problem is solved. Because you know P theta 1, P theta 2, P theta 3, P theta 4. You know mu theta 1, mu theta 2, mu theta 3, mu theta 4. You also know eta theta 1, eta theta 2, eta theta 3, eta theta 4, problem is solved. Because you don't know theta 1, theta 2, theta 3, theta 4, you estimate that. And the way you estimate is you cannot directly estimate the parameter, instead you estimate the mean, eta theta. Estimate eta theta, invert and come back to theta. That inversion you can do because we are working with the exponential family. Exponential family allows you to do that inversion. You don't have to worry whether this is reversible, whether it's a stationary distribution. You don't have to worry about it. The first is parameter estimation. Well, this is like all of these are details. Don't do. Okay. So estimate the parameters. Get an estimate for theta hat of it. Okay. First step is that. Second step, I already told you W star of theta. What is W star theta? We call W star theta as a set of all maximizers. So I showed you an expression for TR star that had a soup in. The outside soup was over the set sigma R, and W star was the set of all such supremizers. Okay, set of all supremizers. So W star theta is the R soup of this particular quantity. This looks exactly like the TR star expression, except that instead of theta, we have replaced it with theta hat n, because we don't know theta. So we simply replace it with theta hat. So you compute the set of all maximizers. Good, that is also done. Third step has two wrappers. One I call wrapper 1, one I call wrapper 2. Wrapper 1 is you draw. So once you estimated the W star of theta hat n in step 2, it's a set. Draw an element arbitrarily from any element values. Call that nu n star. You mix nu n star with the uniform. Okay, mix nu n star with the uniform with mixing parameter eta. Eta is some fixed constant in the algorithm. It's specific to the algorithm. Okay, so eta is some constant fixed in the algorithm, and we mix it with uniform. We get a policy pi theta hat n theta like this, and with this pi theta hat n, we do an outside wrapper. Okay, think of it as a chocolate with two wrappers. Outer wrapper is epsilon n mixture. Inside wrapper is eta mixture. There are specific reasons as to why we do these two levels of wrapping, but essentially you get a policy now. Pi n is a policy. What is pi n? Pi n is a probability distribution on the arms, condition on delays and mass observed states. Whether it is conditioned or not is secondary. The probability distribution on the arms, which means you can use it to select the arms. Okay. So as the last step, we select the arms according to pi n. At time n, estimate theta hat n, get W star theta hat n, get the two wrappers, use the outside wrapper to select the arms. This is the policy. So we can show that under this policy, whatever I had promised holds. The hardest part of this problem was proving this. This lemma says that these fractions of BIAs converge to this set W eta star. I originally wanted convergence to W star. I told you about a point to set convergence that I wanted in the achievability idea. We show that the convergence is to W eta star. The eta is coming because there are two wrappers. Outside wrapper is epsilon n, inside wrapper is eta. As n goes to infinity, epsilon n goes to 0. So the outside wrapper goes away, inside wrapper remains. And the inside wrapper, because of that, we have a eta mixture, which is the inside wrapper. So we converge to this set. Okay. Because we converge to this set, okay. So I'll just so this was like the hardest part of the analysis, showing that this converges. All of this is for selection. So till now I have told you how to select the arms. I should tell you two more things before we complete the algorithm, which is when should you stop? You should stop, otherwise it's useless. So when should you stop and how should you stop? How should you decide when to stop? And when you stop, what is the best arm that you will output? Which among 1 to k will you choose as the best arm? I should tell you this. So in order to stop, we construct a test statistic. I tell you only the high level data. We construct a test statistic. The form of the test statistic is very similar to the form of the inside infimum in the TR star expression. So just go back quickly there. TR star has this inner infimum. We replicate the inner infimum by replacing the theta with the theta hat n, which is the estimated time, and we get rid of q theta r because theta is not known. Theta is the unknown. So instead of q theta r, we use a empirical MDP matrix, empirical transition matrix of the MDP. So that's the test statistic we use. This is the empirical transition matrix. All of this is the same. This is just theta hat. We use this as the test statistic. We couple that with a random threshold, and we stop as soon as our test statistic exceeds the threshold. We just compute this test statistic at every time instant. We also update the threshold at every time instant. As soon as the test statistic crosses the threshold, we stop. At the time when we stop, we look at the estimates of the means that we have done. because of the from the observations we can keep a count of the estimates. We can track the estimates of the means, right? Among all the estimated means, which are the largest, we simply output that particular R matrix. It's the most natural thing we can do. Not the estimated parameter, estimated mean. Because mean is not estimated what is the best. So the largest estimated mean, R which are the largest estimated mean is the best. So is this any good at all? We can show that this particular policy, because it depends on delta. Remember, delta is the error probability which is given to us. You should not exceed error probability delta. Okay. So using the delta in the threshold, algorithm depends on delta. We can show that the error probability is utmost delta. Good. It's a good policy. Does it stop? Yes. It stops in finite time with probability 1. Not just that, its growth rate satisfies an almost sure upper bound, which almost resembles the lower bound 1 by TR star. 1 by TR star was the lower bound. This has only an additional factor of 1 minus eta in the denominator. In particular, you can choose eta arbitrarily small and make the upper bound as close as you want to the bound. Not just an almost sure thing, even in the expected sense, our policy satisfies the same one. So, this is the result that we have. As you let eta go to 0, you get an upper bound which exactly matches the lower bound. Okay. So 1 by TR star was the lower bound that we had established. That was sort of a bad news. Because we said, no matter what policy you use, minimum you are going to take at least so much of time. How much time? Log 1 by delta divided by TR star. At least that much time is required. So can you do the best possible? Yes. We have a policy that matches the lower bound of 1 by TR star only in the limit as delta goes to 3. For any fixed delta, doing the analysis of the upper bound is very challenging. You can derive the lower bound like I showed for every fixed delta. Because you may ask, we cannot get delta go to 0 in the algorithm. The algorithm does not require delta go to 0. The algorithm works with a fixed delta. But in order to do the analysis, we let delta go to 0 and we arrive at this. Okay. So we have matching upper and lower bounds, and this is also the case in the prior works. The prior works have simpler settings. K projects in parallel, you don't make progress when you don't work on a project. Rested arms. That setting and ideal observations, which is a special case of Markov chains. For those settings, there are matching upper and lower bounds similar to this. We were able to achieve the same for restless also. That's the main contribution. So I have something here, but in the interest of time, I'll just skip this. So I'll just leave it at this. This is the takeaway slide. Thank you.
Can you immediately tell how this topic can be depend upon R?
So that was actually what I have on the previous slide. Maybe I'll go there. So what we can show is that, so of course, first notice that 1 by TR star is what governs the stopping time growth. So let's focus on TR star. As TR star becomes larger and larger, this 1 by TR star becomes smaller and smaller. Okay, so that's the idea. Or rather, I think I said it the other way. So, I can say it. So, as R becomes larger, we see the TR star blows. Okay, so the larger the value of TR star, the harder the problem is. Okay, so in that way, I mean, TR it increases with R, TR star increases. Okay, so as we let R go to infinity, this sigma R theta, remember, sigma R theta was the space of all probability distributions on DIA, which satisfied flow constraint and R max delay constraint. Okay, but now as R goes to infinity, we are only left with flow constraint, probability distributions and flow constraint. So one can write down what is the complexity for the original countable state MDP. That is T star. Okay, but the question is this limit TR star equal to T star? TR star is a monotone increasing function. Limit exists, but is the limit equal to T star or not? What's the question? For the general setting, we don't know the answer. Okay, that is for the restless arm setting, we haven't been able to establish this. If we are able to establish this, this is a very good result because it will tell you what value of R to choose. You want the upper bound to be 1 by TR star. So the lower bound is 1 by T star. Let's first clarify that. So the lower bound for the original system, no R restriction at all. Countable state MDP, the original system, the lower bound is 1 by T star. You cannot beat this. So can you achieve this is the question. That we haven't been able to establish. If we are able to show that this is indeed equal, that is, this is actually equal, 1 by T R star, the limit is actually equal to 1 by T star. Or in other words, limit T R star is equal to T star. If we are able to establish that, this will tell us that we can choose an R, however large we want, so that we can make the upper bound very close to the bound. We can, because see, implementing a countable state MDP on a computer is impossible. Okay, you cannot realize a countable state system on a computer which has finite memory. Whereas when you impose this R restriction, you are restricting the state space to a finite set. That can be implemented on a computer. So the question is, what value of R should you use in the implementation? That depends on how far away you want or how close you want the upper bound and the lower bound to be. Ideally, they should be very close. So you better choose a very large value of R. But how large, that depends on, if you want the upper bound to be, let's say 1 plus epsilon times the lower bound, where epsilon is like 0.001, that will determine, let's say R is equal to 10 to the 6, something like that. It depends on how close you want the upper and the lower bounds to be. So that we haven't been able to establish. This, I think this is one of the fundamental questions in this field, which is, does this actually match? So this problem of restricting R, the delays, last observed state, the entire notion of delays and last observed states is not at all applicable to the prior ones. Because when you are working with rested arms, each arm changes its state only when it is observed. So the delays are all equal to 1. That was the hard part, right? In the DI, I is not of worry. It is the D which is of worry, because that is what takes countably many values. The arm delays are all integer values. So the D can take values in the set of integers. That is what we restricted to take values from 1 to R. The delays, the notion of delays is superfluous when we work with rested arms. It is also superfluous when we work with IIT observations, simply because the next observation will be independent of the past. You don't even care. But Markov chain is not like that. Next observation depends on the previous. All of this is there. I hope that answers. So setting the R is the key.
That should be limit, right? Because it cannot be less than equal to 1 by T star theta.
Right. I think I get this way. It should have been the other way. Right? 1 by T R star, the limit comes to 1 by T star. Yeah, setting the value of R is the
Is there any regret result for this?
Oh, there are plenty of regrets. Restless arms were the first study in the regrets. There is something called weighting index policy. So there are index-based policies for achieving regret minimization. There are plenty of works on regret, but as you can see, this setting is completely complementary to regret. So in regret, you can also look at the infinite horizon, for instance. I mean, you can look at a finite horizon T and you can ask what happens as T goes to infinity. Here, it's a slightly different setting. We don't want to continuously keep sampling. We want to stop as quickly as possible. So this is best of identification. It is sort of complementary to regret minimization. And it is also well known that policies which work for regret minimization don't work. And this policy will not work for regret. It's very, very bad for it.
Yeah, because I think we are sampling after R, that
Right.
that will give linear.
Yes, yeah. This is very bad for it. This won't work for it. But it has been studied. The restless arms have been explored more in regret minimization than in the space of pure exploration. This is what is called pure exploration. So regret minimization, exploration versus exploitation. This is pure exploration.
So, if there are no more questions, we can close the session. Thank you, Dr. Karthik.
Yep.
And if there are any questions outside, please help yourself.